Hello, welcome to this another video. In this video we'll be solving the design of adding and searching word in an optimized data structure. The problem requires us to add some set of words and then search for it, and we have to make sure that we are able to search in the most optimized time possible. Here's an example. But there's another one small constraint in this problem, and that is during the search process we may encounter a wildcard like the dot operator, which says whenever we see a dot we just ignore that particular character at that location. Let's better understand the problem with the help of an example. Let's just say we have some set of words to insert, which is MAD, mad, and then followed by BIT, bit, but, and bot. Okay, we have these four words, and now if we had to somehow store these set of words and then search for it, obviously from our background knowledge we can think if we can sort this, then we can probably use the binary search algorithm to search for the target element from the sorted list of characters or set of words. But it will work, but given that we have a constraint of dot operator, like we are trying to search b dot t, we don't know what this dot can have, so we don't have a prefix to kind of search in our binary search algorithm, but we can definitely modify the algorithm and find a way. But another data structure which particularly helps us in problem like this is the prefix sum, or is the prefix tree, or very generally called the Trie data structure. So in this video we are going to solve it using the Trie data structure, and in order to look for the solution, let's just try to understand how a trie would store these words. Whenever we want to insert a word mad into our trie, it would, on the first level it would say, oh, I'm seeing an M, and then followed by the next index it said in the next place I see an A, and in the last place I see a D. So we have MAD, and it will relate it and form it in the form of a tree data structure, and hence the name. And for next, when we want to insert the next word bit, it would say in the first layer I don't see a B, so I will insert a B, and then in the second word it says, oh, I'm not seeing an I, so it will insert a I, and next in the next word it says I'm not seeing T in the last end, so I'll insert a T again, followed by the relations, of course. And then when it comes to the next word, BUT, now in this case we already have a B in the level 0, so we don't have to insert, we'll just go with the existing character that we already have in our trie. And in the next character space we have a U, but we do not have a U in the second space, so it's important that we insert a U in our second place and establish that relation in our trie. And in the next or the last character, we know that it's already there or present in our trie data structure. That means we can reuse that given character. Followed by BOT. O is not present in the next or the mid layer, so I'll insert an O and then establish that relation. Notice that there are two advantages. One is obviously during the search process we have the advantage. We'll try to understand with an example later. But you see, just by applying the principle of storing based on a trie, we are not repeating the characters that we have already seen, thereby saving some space. So there is that advantage when we use a trie. So addition works this way. Now, how do we search? Let's say we want to search a character called BAD, a word called BAD. So first thing first is that we'll go to our first iterator. We're trying to match a word B, and this is our first character, and this is our first level. So we want to search the first character in our first level. So do we have a B in our first level? Yeah, we have a B here. So that means we can move on to the next element. So we'll go to the next element, which is A here. And since it is the second index, or the one index in Python, or the second index, let's just generalize. So we have to search it in the second layer of our trie. And we don't actually search the entire layer. Rather, we know we have B here, so it should be somewhere within this subspace rather than the entire subspace, because there's no relation here. So we are only going to go down this path or this tree, and we'll say this is where our word can exist. And we are right. We can search within this range. We don't see A. So if there is no A, that clearly means there can not be a matching word found in our trie data structure. So let's try it with another example. Let's see with BUT. Now in a BUT we say, okay, the first index needs to be compared in the first level. So I see B here. So it's time to go down this path. And in the second index I see a U, and we have a U here. So this is selected, this is selected. So the only path that we can go is a T. And luckily in the third element we have a T. So we can return a true, stating that we have the word BUT. Alright, so search works this way, where we find a particular path. It's like a tree traversal. We find a word and go down the path and see what that path has to offer, all the words that can be represented, while making sure that we go down those paths. Okay, but here's a challenge. The challenge is that this particular problem tells us to search for a word when one of the given word is a dot, right? So how do we solve that? Now it's pretty easy. If it's a dot, we just ignore the comparison process, because it could take any value, and we support all the values. It's like a wildcard. So when it comes to a dot in the first level, I don't mind. But the problem is, next in the second index we have a U, and in this case I don't know if I should go down this track or I should go down this track. There is an ambiguity at that particular point in time, and you can think many possible solutions, but this solution is going to be old school, and that is to exhaustively search in all possible pathways. So you have to take all these paths and see if you can find the second word U. That's a lot of manual effort, but that is mandated as part of the search process when it comes to the trie data structure. But nevertheless, it's more economical when you compare it with other forms of search operations. So with this set of examples, let's just move on and try and implement a trie. And before that, I would like to bring your attention to two things. That is, how do we represent a trie? So this trie, in order to represent it, we need two things. So representation is going to have two important things, and that is a trie node class requires one, it needs all these elements which you can represent as an array or a map. Okay, so I'm going to call it a children. It could be an array or it could be a map. The second one is called is end flag. So notice that in the end, while searching, if we hit the word D, it should tell the algorithm that we have a potential end of a word. So if it's an end of a word, if we mark it during the search process, we understand, okay, at this particular point, a complete word is found. So at that particular point, we can say, okay, if we are trying to search for such a word, this word does exist in our trie, right? So in order to write this more formally, I'm gonna say in a programming language construct, I'm gonna say we will have a trie node, yeah, and that there's going to be a class, and inside the constructor it's going to have two important members or attributes, and those are a children, and I'm gonna follow the Pythonic constant. It's going to be inside a constructor, which I like the map representation because we don't waste storage here, but there is a lot of people who go with an array initialized from 0 to, it has 26 characters. So an array multiplied by 26 in Python gives you a big array of 26 elements. You can have that as well. One place for each of the characters from A, B until Z. But we're going to stick with map implementation for this video. So we have self.children, which is a map, and then in the end we have a flag which says if this is the end of a word, which initially it's a false value. So this will be our trie node. All right, let's just jump into implementing this particular solution in our Leetcode. Here we are in the coding panel. So before we go and implement this into our function, it's important that we create a new class to represent our trie node, which will initialize two important attributes as we discussed, and that is going to be the children first. So self.children is going to be the first attribute, which is going to be a map in this video. It could be an array if you want it. And then we have a flag is end, which represents the end of a given word. Okay, so two attributes and our class is done. Now in order to initialize our word dictionary, we're going to say self.root is equal to a new element, which is new object of the class trie node. All right, so we have initialized a new object, and in this object we are going to add words. So whenever an add word is invoked, we'll have a temporary pointer. And remember, why do we need a temporary pointer? So every time we want to insert in a word, we go next into the word. So we'll have a temporary node pointer which is initially set to the root value. Okay, and then as we go down the iteration, we'll go one step next, just like a linked list. So now I'm going to say to insert all the words, I'll take for every character in my word, I would see if that character is not already in my node.children map. If it's not there, then I need to insert it. So node.children of that particular character needs to be initialized with the new trie node. All right, and now in the next place we have to go to the next node. So node will be equal to node children. Specifically, we have to select one path. There can be multiple branches, but we have to take one path. In B we have IUO, we can go in this track, or we can go to M. From M we can go to A. So from level 1 we could either go to A or IUO, and particularly a particular element. So for that we have to say node.children particularly at that character. So that's that in implementation helps us to go into that particular path that we want to. And finally, after the entire word is inserted, we say we'll set our flag node.isEnd to be equal to true, and this will help us a lot in the search process. All right, so that is our adding the word. Now for search, now I told you that there is a complexity which arises with the dot operator. So in one of the previous, in a very simple try problem, it's very easy. So we will pretend that the complexity does not exist for now. The dot operation does not exist. So if dot operation does not exist, how do we do it? It's very simple. It's going to be, what do we want to do? We just want to check if we are able to search for the given word. I'm going to backtrack and all right, let's go. So if the word of that particular index, okay, so or the character, and let's say we are in a for loop, for every character in our word, all we need to do is check if the word or if the character is not in the node.children, right? If it's not there, there you go. If it's not there, it's written false. And what is our node? Initially our node is the root value, right? Node is equal to self.root value, and then we have to increment the node value. If this condition does not exist, if that is false, we say node, go to the next element. So node.children of that particular character, and let's do the same process next. Take the next character. If it's not there, written false, otherwise move the next pointer. So at this particular point, if all these words are found, we can simply return the last node's flag is end. Now note that if the last element was actually the end, we would have, in the insertion process, we would have marked that to be true, right? So we can just return that particular attribute of that node, and that would say if it's really the end of the word. If that's true, it says, oh, I found the word. If not, it's going to be a false. Now we hit upon a condition where we were given a dot operator, right? So in order to solve for that, I told you we have no other choice but to brute force and try and find in all of the branches. So in order to do this, I'm going to modify my code. I'm going to delete this and write it from scratch. What I'm going to do is introduce a helper function search, and I'm going to think of this search process like a depth first search in a tree or a graph. So it's very similar. That is my construct here. It is going to be a depth first search based algorithm with the base case. If the index is equal to the length of the given word, all you need to do is return the node.isEnd attribute. That will tell you if it is true or false. Now there is a special condition, and the condition is that if the word at the given index, if that is equal to dot, I'm going to behave differently. I'm going to pass it now, not going to implement. Otherwise, I'm going to follow the implementation that I just discussed earlier. That is very easy, right? I'm going to check if the word at that given index, if it is not in my node.children, I can immediately say I can return false, right? But if it is found, then it's time to search for the next word. Okay, so in order to find for the search word, I'm going to invoke the same helper function, which is a private function search, and I'm going to search for the index is going to be index +1, and for the word, it's going to be the word, and for the node, it's going to be the node.children of the next character. The next character was word of index. Okay, it was just next character. All right, that's it. Now we are coming to our special case. What if it's a dot? And I told you, if it's a dot, we have to explore all the paths. So how do we do that? In order to do that, we just say for every child I see in node.children, it's a map, and map has many children. Map has collection of all these childrens that we have added during our add word process. So I'm going to say node.childrens.values. That will give all the values that are stored inside the map, and I'm going to traverse through each of the children. So I'll go and invoke the search operation on all of the childs, and if the search process for the next word, of course, for the current word, I'll not search for the current word. This is something that we have to pay attention to, because the current word, it's a skip. We don't care whatever it is. So index +1 should same word should match with the child value. Well, if I find my next word, or the word of index +1 in this given child, we can immediately say, hey, return true, or at this index. Okay, we can say it's return true and then return false otherwise. If we don't find an element, we can say return false, and we return false when after following the entire process we exhaustively search all the paths that we can see, and if we don't find it, once it exits the for loop, which says I couldn't find the given character, index +1 character in any of the child, then I would say, okay, I'll return a false. All right. So this is one complication when a dot is introduced. We really don't know which track to take, and so we do a for loop. We take all the node.children values, I, U, O. We take all the children value from the root element. So MB, we say there is a path going to A, and there is a path going to I, U, O. So we have to check in all of the child's value, and we see if we are able to get that particular character at index +1. So with this, we have to invoke this private function. We have defined this private function inside. So I'll come right here and call the function, and we can just return whatever this function returns to us. So initially the index is 0. The word is as given to us from the input. The initial node will be our root element. So from our root element, I'll call the search function, and it will have some base conditions. If it is dot, explore everything. If it's not a dot, follow the simple process. Just check it. If you have it in children, no problem, go to the next word. So how do you go to the next word? It's like recursive function. Just index +1, and then node, just increment the node value and search on the next track. So it's as simple as that. If it's not a dot, if it's a dot, then explore all the value. If you find it, just return true for the given iteration and go on to the next value, right? So that's how we solve it. All right, with this, we'll try and run this and see if you're able to get the output. I already tested it, so it's going to be just doing it again for the sake of it. But here we go. We have the solution, and it beats 82.98 people. So it's one of the very optimized way, other than using some other algorithm based on binary search. So with this, we'll conclude the video. See you guys in the next video. Bye bye. See you.